Recording. So we start right here, and we started with the stress life method equations. So I'm going to continue with that, and most probably Thursday we can try the problems. We'll do a small revision for your exam just before you leave for the break. Just 1 second. Oh. All right, so let's write. We started with stress life method equations. Okay, before we start with the equation, we go through material properties first. Equations for material properties. So what is the main material property we will be interested in fatigue applications, endurance limit for steel? So first we are going to see the equations corresponding to predicting endurance limit for steel, material steel in particular, and we will extract this from certain empirical equations. What are the empirical equations for steel? We are going to write the endurance limit for an ideal lab specimen with the symbol SE prime. So when I use the prime with the S symbol, SE symbol, then it means this is lab specimen, ideal specimen rather. So the lab specimen is highly polished and it does not have any rough surfaces as the components which we will have in the field, okay, or in the operation. So rather this is a lab specimen, ideal specimen without any surface defects, and for such a specimen SE prime is provided by the formula 0.5 SUT. What is SUT? SUT is the ultimate tensile strength of the material, specifically steel, and this is true under one case if your SUT value is within a certain limit. Okay, SUT is less than 1400 megapascals. Okay, in that case, so we can use less than or equal to here in SI units. Otherwise, it is equal to 700 megapascal if SUT is greater than 1400 megapascal in SI units. If you are looking at in English units, you will take it as 200 kpsi, and that is the limiting point. So we have got this empirical equation just to estimate the value of SE prime. Okay. Now, to know what is the finite life of a specimen, okay, if you recall, from the SN diagram for completely reversed loading, so second one we are going to see is SN diagram. Again, this is also called Wooler diagram, named after the person who first conducted the experiments here. So let's see here. Yes, number of cycles to failure, and for a typical materials such as BCC materials such as steel, we have the existence of endurance limit. It flattens out, below which the life is infinity. That's the prime value. And here what we see here is below SE prime, here in this region, we have infinite life. If your stress is less than a C prime value, we have infinite life. So in other words, this is usually 10 million cycles or 1 million cycle, 10 power 6, 10 power 7, 10 power 8, etc. So remember, we have it on the x-axis in the log n scale. So if our life is 1 million cycles or more, we can consider the life of the specimen is infinite. However, if we are between, this is 10 power 0 cycles or 1 cycle, and let us say this is 10 power 3. If we are between 10 power 0 and 10 power 6 cycles, then we have a finite life. In that case, we have to do a curve fit between S and N values. So the curve fit between S and N values is very similar to the strain life method, where we had the equation, if you recall, within the elastic limit, we had this kind of relationship from Coffin-Manson relationship. We will use that relationship and obtain the equation 6-9. Okay, so basically we are obtaining the relationship between S and number of cycles to failure, and this is the formula for obtaining the number of cycles to failure. Now this formula is not complete yet. So there are two regions here. One, the region between 10 power 0 and 10 power 3 cycles. The curve is different. So let's go back to the SN diagram. If we have seen before, I'm going to go to show you how the curve looks different. So this curve is looking different. So for this part of the diagram, there is one S versus N relationship, and between 10 power 3 cycles to 10 power 6 cycles, we have a different equation. Okay, so there are two equations, two sets of equations we are going to derive. Again, before we go there, first we are going to derive for this region what is the relationship between S and number of cycles to failure, especially between 10 power 3 and 10 power 6 cycles. So let's go back to that equation and see what they are going to do to 6-9, equation 6-9, where we have to figure out what is this strength coefficient here. Okay, fatigue strength coefficient and the fatigue strength exponent. Okay, so we take that equation, rewrite it here. What we can say at 10 power 3 cycles. So at 10 power 3 cycles, we can rewrite the equation as f prime at 10 power 3 cycles should be equal to sigma f prime 2 times 10 power 3. N we have to substitute as 10 power 3 cycles raised to the power b. Let's call at 10 power 3 cycles, let us assume it is equal to some fatigue fraction f. So we are going to call the small f as the fatigue fraction times SU2. Okay, assuming this is the equation. From this equation, we can get a form of equation for fatigue fraction f, which is sigma f prime over SU2 times 2 times 10 power 3 times b raised to the power b. So we get one equation for fatigue fraction. So let's write this equation here. So this is another equation we will be using to get the number of cycles to failure for a completely reversed loading. Okay, so this is very important, completely reversed loading. What is completely reversed loading? Sigma mean value is always 0 in the complete reversed load, while sigma A is some finite value, which is given by sigma max minus sigma min over 2. And we also know that in completely reversed loading, sigma max magnitude is equal to sigma minimum magnitude In other words, we can also write sigma max is equal to minus sigma min. So that gives us, for completely reverse loading, sigma A is equal to sigma max. If you substitute here, you will get sigma max here. Okay. So in the completely reverse loading, this is the case. For this case, first equation which we will be using in prediction of life is the fatigue fraction F. Fatigue fraction. So what is this equation? We are going to write it here, sigma F prime, which is the fatigue strength coefficient divided by ultimate tensile strength, which usually we will get it from some tables, and then 2 times 10 raised to the power 3d. So to find the fatigue fraction F, we need sigma F prime. We also need fatigue strength exponent. So we need two equations for this. There is a way to estimate what is sigma F prime from the SUT value, especially for steel, which has a Brendan hardness value less than or equal to 500. So if your steel material has a Brendan hardness value less than 500, then we can use the equation, these two equations. One is in the English units, one is in the SI units. Mostly we will solve problems with SI units. So we write this equation, SUT plus 345. So this is an estimate. Usually estimate from, everything is in megapascal. So we got sigma F prime. We can find fatigue fraction, but we also need B. Okay, to find B, substitute the endurance strength and the corresponding cycles into equation 6.9 for and solve for B. So we take the 6.9 here. We substitute endurance strength. So what we do here? So this is very simple. We take this equation, SF prime here for 10 power 6 cycles will be actually equal to your endurance limit. Remember, we already had an equation to estimate endurance limit. So we are going to put SE prime here. Should be equal to sigma F prime, which we have already figured out how to estimate the value from this equation, times 2 times 10 power 6 raised to the power b. So the only unknown here is b. Now we can take log both sides and then we can figure out what is b. So why do we need these values? These values are required to estimate the number of cycles to failure. So this is why we want to do this. Okay. So B is equal to minus log. If you take log both sides and simplify that, this is what you are going to get. Let's see, prime divided by log 2n. Log 2 times NE, it is written as NE, number of cycles at endurance limit, which is 10 power 6. Okay, so this is the equation. So here, what is the main quantity we have found? Fatigue fraction. Okay, so we have found fatigue fraction. So I'm just putting this so that this is the important result we need to calculate in stress life method. Okay, so once we find this fatigue fraction, then between 10 power 3, first we need to get the equation when your number of cycles to failure is between this limit, then we need to get the equation between SF and and the number of cycles to failure. Again, we go here between these 2 points, between 10 power 3, 10 power 6 cycles, we want to get a curve fit between SC prime and number of, sorry, not SC prime, SA value and number of cycles to failure. So what is the equation? I'm not going to derive this equation. This is the next very important equation we have to deal with. Okay. In stress-like method, this is the important equation. So directly we are going to write this equation, and this is very important. SF is equal to A times n raised to the power b. So this is the equation we will be using to figure out the number of cycles to failure if it is between 10 power 3 to 10 power 6. And A is given by this equation, where small f is your fatigue fraction, which you find by the above equation given we just derived before. F times SUT the whole square divided by SE value. Okay. Now notice that this is SE value. We will see how to estimate the real SE value from SE prime values. So SE is usually not equal to SE prime. Okay. So this is A and B. How do we find B? Minus 1 over 3 log, and we write it FSUT over S. Okay, so this is the important equation for a completely reversed loading. We can predict the number of cycles to failure using this equation, especially if we know what is the amplitude of stress we are applying on the component. So usually we will know what is the load we are applying on the component, and we will be able to evaluate sigma A. Your sigma A is nothing but is your SF here, SF value here. Once we know SF, we can calculate fatigue fraction F from the equation given here. Once we calculate what is fatigue fraction, then we can calculate what is A and B values, and then substitute here and figure out what is F by taking log on both sides here. Okay, so we will see an example problem how to use that. Okay. We can write the same equation, okay, in the inverse here. Yes, SF is equal to A times n power p. If you invert it, this is the equation we get. Your SF is nothing but your sigma A value, completely reverse cyclic load. What if it is between 1 to 10 power 3 cycles in the figure what we have seen before? SL diagram. So we have seen what is the equation to use between 10 power 3 and 10 power 6 cycles. What if it is between 10 power 10 power 0 and 10 power 3 cycles, between 1 to 1000 cycles? We have to use a different equation, and this is the equation we have to use. Again, the fatigue fraction F is being used there. This is another equation for completely reverse loading. We have to use. This is an approximate way to predict. Okay. Now, usually when we are in this region, we will use the strain life method rather than the stress life method. But this is an approximate way to figure out what is the number of cycles to failure. And a more accurate method will be based upon strain life method rather than stress life method within this range, because this is low cycle fatigue. especially if plasticity is involved, we should do strain life method. However, there is an approximate way to calculate, and the way to do this is using this equation, the SF. Look at here, we do not have an equality sign, rather we are specifically saying it is greater than or equal to, your SF value is greater than or equal to SUT. So this will be the perhaps the maximum number of cycles to failure based upon this equation. Okay, SUT times n raised to the power log f over 3. Over. Okay. Now, notice that we are using log everywhere. What is this log? Is it natural logarithm or logarithm to the base 10? Just look at the equation here. Our number of cycles to failure are always written as 10 power 3, 10 power something. So this is log base 10. So realize we are doing log base 10 and not natural logarithm. If it was a natural logarithm, we would write it as LN. We don't write it as LN wantedly because this is base 10. Okay, this is log base 10. Here, everywhere we use log, this is base 10. Here also 10. Okay. So even in the equation where we find fatigue fraction, if you find any log values, again base 10. All right. So this is clear. Any doubt here?
Doctor,
You guys clear? Okay.
will the
Yeah.
question specify the region?
What? Repeat.
Will the question specify which region the n is? Like it is in the
Usually, if you're
between 1 and
we can
1000.
yes. So usually, what we will be the data we will be giving is the yield strength value, the SE value, SUT value. So these two values will be given. Let's say SY and SUT value. Using SUT value, you can find SE prime, correct? So depending upon SE prime value, you will know at least whether it is infinite life or finite life. If your amplitude of stress which you are applying on the component is greater than SE prime, then definitely finite life. All you need to know is whether this is between 10 power 0 to 10 power 3 or 10 power 3 to 10 power 6 cycles. So how will you know that? You can compare it with the yield strength. If you are very close to yield strength, most probably your number of cycles to failure is here in this region. Okay, but you are significantly less than the yield strength, your amplitude of stress for a completely reverse loading, then you are in this region. So you can reasonably come to a conclusion whether you are in this region or this region. Okay, clear?
Yes, clear.
Okay. Also, you can compare with SUT value. If you are near SUT value, definitely you are here in this region. 100% you are going to be in this region, and then we can approximately predict what will be the maximum number of cycles to failure using this equation. However, it would be correct to solve the problem in this case with strain life method, because for strain life method is especially suited for your low cycles application. Okay. Okay. So let's go here. A simple example problem. Always remember the equations which we have seen, they are for completely reversed loading. Again, all these examples They are for completely reverse loading. What is a completely reverse loading? The mean stress is 0, like sinusoidal waves here, where you have sigma mean equal to 0 and sigma amplitude equal to sigma max. When this is the case, then only then you will use any of the equations given above. On the other hand, if you have a load like this, which is not completely reverse loading, then you will never use those equations directly. If you have a load like this, don't try to use. So this is your 0 stress point, and let's say your mean stress is some 10 megapascals. Don't try to use any of the equations which we have seen above to predict the number of cycles to failure. We have to convert these problems to this problem, and then we can use. Convert it into equivalent completely reverse loading problem, then we can use the above equations. We will also see this part later, but for now we are going to concentrate on completely reverse loading cases only. Okay, so all these problems are completely reverse loading. Given a 1050 hot rolled steel, estimate the rotating beam endurance limit at 10 power 6 cycles. So when you are given what is the material, this is the standard according to the ASI standard, perhaps 1050 hot rolled steel will have certain properties. How do we know what is the property for this steel? For that, we need to go to the book and we will look at the appendices for certain properties. Let's see here what they have. That matter, appendix. We need the material properties for certain kind of materials. Let's see here, mechanical, which one? We have here A20, some heat treated hot rolled, so heat treated steels perhaps we will find in A21. We also have a couple of other tables. For example, you can see A27 fatigue life strengths for selected plain carbon steels. So some of these tables may be very useful in our problems. So let's go to table A21. We're already in the appendix. All these tables will be provided for you in the exams. So 1050, so we can see 1050 here. Tensile strengths we are given, these are heat treated, so perhaps not this particular table. Let's go back to the figure here. It will directly give us the table A20. Okay, so let's go here. A20 is minimum and yield strengths. Okay, so let's go for A20. A19, A20. Okay, so here we have hot rolled and SAE and ASI numbers 1050. So this is your 1050 hot rolled steel, and we have the value tensile strength in megapascals. In the bracket, it is given in KPSI. Go back to the problem. They are working out in KPSI, but we will work it out in in SI units rather. Okay. Let's work there. The example problem is 6.2. Example 6.2. So first, the question, what is the question which is asked in the problem? The rotating, first we need to estimate what is the endurance limit. Okay. So problem one, endurance limit. SE prime, you write with question mark. So first we need to find UT value, ultimate tensile strength, which we found it to be 620 megapascals. 620 megapascal. It is less than 700 megapascal. So using one of the formulas what we have seen before to estimate the SE prime value, we have to use 0.5 times SUT. This is the formula we need to use to estimate what is SE prime. 0.5 times the SUT value, and you get half of 620, 310 megapascals. Okay. So this is an SI unit. The endurance strength of a polished rotating beam specimen. Okay, so what is the okay? So okay. So what we are asked here, corresponding to 10 power 4 cycles to failure, what is the corresponding we should not call it. Okay, so we can call it endurance strength or fatigue strength. What is this quantity which we have found? This is endurance limit. Endurance limit. Okay, we do not call it strength. SE prime is endurance limit. Any value which is associated with finite number of cycles to failure, especially the sigma A value associated with finite number of cycles, is called as endurance strength or fatigue strength. So the second question we are asked is fatigue or endurance strength. Okay. So at how many number of cycles to failure? 10 power 4 cycles to failure. So what is the equation we should use? The equation we should use is, if you recall, SF. So again, let's go back to the equation we have written. Since it is between 10 power 3 to 10 power 6 cycles, 10 power 4 cycles to failure, this is the equation we need to use, SF. Okay, fatigue strength is equal to A times N raised to the power B. Now we need to find what is A and B, but A and B values, to find A and B values, we have seen in the formula above, we need what is called as the fatigue limit F. So first we start with this equation, fatigue limit. To find F, we need sigma F prime and also the B values to be estimated first. So let's use that. Use those equation. So to find that, first I write sigma F prime is equal to SUT plus 345. All the equations which I have listed plus 345. All these are estimates, empirical formulas, not based on theory, but purely based upon empirical theory for only for steel. Any other material, don't use this equation. This is only for steel material. 345. So what do we get? 5 here, 6 and 6, 7, 9. 965 megapascal. So this is your sigma F prime. Let's go back to that equation again and estimate B. B will be equal to negative log 10 sigma F prime over SE prime. We have a big equation. So don't use, okay, so this, let me put a bracket here. All these calculations are fatigue for only for fatigue fraction. only for fatigue fraction. Okay, the calculations which I am doing here, they are only for fatigue fraction, and the B which I am going to calculate here, don't use this B value over here. Okay, they are different. This B value is going to be different, so I'm going to put BF just to avoid any confusion, and write minus log base 10. So let's go to the formula here. Sigma f prime over SE prime, and we have 2 times 10 power 6. Log base 10, 2 times 10 power 6. Hopefully this is right equation. I have copied. No, here, no. Okay. Let's substitute, and one of you can calculate if possible. So log base 10, 965. What is the SE prime value? 310, which we have estimated already in the first section. We have 2 into 10 power 6. Anybody?
1 minute, doctor. I will calculate.
Okay.
I got, doctor, negative 0.078.
After 8, what do you
2.
have? 2.
3,
7, 8.
3 approximate.
Okay, so let's write it as this. Now we can estimate what is fatigue fraction F. Remember that we are doing all this to estimate the value of fatigue fraction. So what is the equation for fatigue fraction? We have it here, sigma F prime over SUT. SUT, and let me go to the slide and open up that equation here. That way it will be easier for us. 2 times 10 power 3 raised to the power b. Substitute sigma f prime, SUT and b here, b values here, and first find the fatigue fraction f. We have 965. SUT value is 620. That's the value, right? Yes, 620. Times 2 times 10 power 3 raised to the power b, which is negative 0.0783. So what is the fatigue fraction?
0.8583.
0.8583. So this is the, we have only found fatigue fraction here. Now we have to use the fatigue fraction in this original equation to find what is the SF value, which is the question asked, fatigue or endurance strength at 10 power 4 cycles. So for now, we have to again you calculate A and B values to be used in the other equation. So let's go down here. Now we have the A equation. For that we have to use 614 and 650. F times SUT square. F is 0.8583. SUT value is 620 square divided by SE value. SE value we predicted to be 310. So that will give us what is A value. And then similarly B, B has to be found out using this formula minus 1 over 3 log brackets open F times SUT 0.8583 into SUT value divided by SE value, which is 310. Remember, all this is base 10. When you use your calculator, don't use natural logarithm. You have to use base 10. Did you use base 10? Who was
Yes,
the person?
doctor.
Okay, all right. Don't use by mistake natural logarithm anywhere.
A value, doctor, is 913.4818.
4818. Correct? 913. Correct?
Yes.
Okay. What about B?
Negative 0.0782.
Okay. All right. So we have A and B values. Now we can use to find the problem SF. Yeah, 913.4818 multiplied by number of cycles to failure here is 10 power 4 raised to the power B. It is minus 0.0782. So what's the value we get?
Triple 4.5288.
Okay, so megapascals. So this is the corresponding value of SF. So if we are, let's go back to the figure and let's see here. If you look at this figure at 10 power 4 cycles, we are here. We find the intersection point over here, and corresponding to this intersection point, if you draw a horizontal line, and this value in the SI units comes out to be 444.5288 megapascals. So if we apply this value of amplitude of stress on completely reverse loading, again this is completely reverse loading, if we apply this amplitude of stress on the component, then the number of cycles to failure will be 10 power 4 cycles. This is what we have found. So sometimes you would know in your application, you want at least a life of 1 million cycles or 10 power 4 cycles for your particular component. What is the maximum amplitude of stress I can apply on the specimen? So if I ask that question, we can find it through this equation. Through the equations where we first figure out what is the fatigue fraction, then A and B, and then use SF is equal to A times N raised to the power B, and then solve for it. Now, carefully remember that there is a B which we calculate to find out what is the F value, fatigue fraction value. Do not use this B value in the equation for SF directly. Okay, there are two different B values we have to consider. Is that clear?
Clear, doctor.
Clear. Okay. So let's go to, we have solved this problem. This guy, he has used it in the English units. We will solve everything in SI units. Okay, so don't worry about it. But the values are almost same, I guess. For fatigue fraction, we got the same kind of value. And if you convert it megapascals into kpsi, you will get the same values. Let's go to the third problem. The expected life of clearly written polished rotating beam specimen. That means this is a lab specimen. Okay, and we have to use the SI prime values under a completely reverse stress 55 kpsi. So what would be the expected life of the component if I apply on the component an amplitude, completely reverse loading, an amplitude of stress equal to 55 kpsi. Okay, so since they have given the value in kpsi, I'm going to convert this online, okay, into kpsi into we want the value in megapascals. Let's see what's the value we get, around 379. Let's take 380 megapascals. So for 380 megapascals, I want to find, I'm going to write it here, equivalent to, approximately equivalent to 380 megapascal. I want to find what is the number of cycles to failure in our problem. So which means what? My sigma A, which must be equal to this, is equal to 380 megapascals, but we have to use A times n raised to the power B here, sorry. And we have already figured out what is A and B for the particular material. We just use those values on the equation here. So, and then solve for number of cycles to failure. 380 must be equal to 913.4818 multiplied by n is unknown, raised to the power b minus 0.0782. So how do I find n here? Invert this formula. There are a couple of ways we can do that, very easy. We can write n raised to the power minus 0.0782 should be equal to 380 over 913.4818. Now to find n, what do? I raise to the power negative 1 over this value, both sides. Okay, if I do that, if I divide in the exponent by the same value, I will get n power 1 here. But on the right hand side, I am going to get 380 over 913.4818 raised to the power minus 1 over 0.0782. That's all. So find the n value here. What is the n value we get?
$74,310.889.
Okay, so let's write 889, approximately 74311 cycles approximately. Let's see. So maybe some slight, because we considered up to a certain number of digits. That's fine. So based on that, we get almost the same value, 77,500 cycles here, 74,310 cycles. Now, why do we have the small difference? Most probably, this guy, he assumed f is equal to different value, 0.86. What is the value we have? Fatigue fraction. We have much more accurate value here. That's why. How did he get f is equal to 0.86? He got it from a graph. So f you can calculate accurately from based on the equations which I have given already, or if I provide you this graph. Okay, this is on the y-axis we have f, on the x-axis we have SUT value. So using the same equations, this guy has plotted this graph, and from this graph for 620 megapascals, or what is the SUT value in let's say in the English units, we have SUT equal to 90 kpsi. So equivalently we go here to 90 kpsi, and he has assumed approximately 0.86. Okay, So that's why we have some difference in values, that's okay. So it is more accurate to calculate with the equations. Okay. Now there are additional equations which we have to care about. We will see that after 10-minute break. You can come back at 9:05 a.m. and we will continue the class. So we'll have a small break now and we'll come back at 9:05. See you guys. 9:05 a.m. Can you guys see my screen?
Yes, doctor.
Okay,
Yes.
let's continue now. Okay. Okay, so now the next stage is how do we deal with specimens which are not lab specimens. That is, there are some scratches on the surface, maybe there are some corrosion effects. So all these factors, extra factors, they also influence the endurance limit of the specimen. Okay, so we are not dealing in practical situations or applications in components. We are not dealing with ideal lab specimens. Rather, we are dealing with components which have various sizes, various geometries, etc. And we may apply loads, different kinds of loads, not a ideal bending moment load. So how do we deal with specimens or components like that? Okay. So for real specimens or components, we have to use the value of SE, the endurance limit, the correct endurance limit, rather than the laboratory value of the ideal specimen. Okay, so it has to be modified, and the endurance limit is modified by 6 different factors, which are called as Merin factors. These Merin factors, they depend upon various conditions. For example, Ka here. Notice that for Merin factors, we always use the small k, while for the stress concentration factor, so this is the Merin factor. If we are using stress concentration factor, we use capital K. So don't get confused between these two terms. When in exam, I will if I give you capital K value, it means stress concentration factor, and there is also capital KF. Here also we have small kf. When I use small kf, it means it is a Merin factor. If I use capital KF, it means it is fatigue stress concentration factor. Don't get confused between the two. Every semester, students confuse between the two values and they mix up. Don't do that. Okay, again, capital KF is fatigue stress concentration factor. Small k are always used for Merin factors. Okay, now let's continue. If you take Ka, for example, this is the surface condition modification factor. Why is the surface condition so important? If you take fatigue and if you have cracks on the surface, and if you recall what is fatigue, all fatigue problems start with cracks. Somewhere micro cracks is present, and from micro cracks, fatigue phenomena start, right? So surface condition is extremely important. And based on that, the endurance limit of the specimen changes. So Ka gives an idea about how the endurance limit of the specimen is affected by the surface conditions. Kb is size modification factor. Why do we need size modification factor? In a lab specimen, we have a particular size specimen. There is an ideal size. Based on the size, we did the experiments and then we came up with the values Se prime. However, the size, if the diameter is larger or smaller, then the Se prime value which we extracted from experiments cannot be used directly. It has to be modified by the factor Kb depending upon the size of the component. Then we have Kc, which is the load modification factor. Why do we have load modification factor? It depends upon how we extracted Se prime value. Did we apply tensile compressive loads and then extract Se prime value, or did we do a bending moment load and then extracted the Se prime values? So depending upon how we did the experiment, and depending upon what kind of load is applied on our component in real situation, depending on that, Kc value will change, and Kc value modifies and gives us the correct Se value here. Then a lab experiment is done at room temperature, usually at room temperature. But if we are operating at a different temperature, again the Se value is going to change, and Kd value takes care of that depending upon what kind of temperature we have. Then Ke is the reliability factor, usually provided by the manufacturer. Reliability, it could be 50% reliability, 90%, 95%, etc. There is a table available for the reliability factor, and based upon reliability factor, Ke values are also given, and depending upon this reliability factor, Se value again changes. Kf is miscellaneous effects. It could be corrosion, it could be some other operating conditions and physical factors which can again change the Se value. Okay. Usually we do not get the Kf values. These are to be experimentally determined, and because of the difficulty in determining the factor Kf, in all our cases, Kf is assumed equal to 1. Okay, in all our applications. Again, this Kf, small kf, is a Merin factor and not the fatigue stress concentration factor. They are different. Okay. Okay, so Se is the endurance limit based upon all the conditions above, and it could be given at a particular location, critical location for a part. Okay, all right. So what are the equations to be used? Again, these are all empirical equations, and especially for steel in particular, this is the equation we are going to use, and this is the data we are going to use. All these formulas and tables will be provided to you during the exam. Nobody expects you to remember all these formulas. Okay, and you will directly use them. So the A value, for example, it is given in English units, SI units. Mostly we will be solving in SI units. So these are the values to be used along with the exponent value here. The COT value, you can extract it from the table A20 as we have seen, and if it is heat treated, A21. Okay, from these two tables we can extract these values. These tables will also be provided during the exam. So directly substitute the values and we can get the value of Ka. I'm not going to solve these problems. These are very simple. Just directly apply the formula and calculate. Kb. Okay. Kb is the size modification factor. In your lab specimen usually has a circular cross section. What if you have a rectangular cross section? Then you have a problem here. How do we deal with rectangular cross sections? There is a way to deal with it, but before we go there, Kb is empirically evaluated through these formulas, again in English units, in SI units. So the D value here has to be substituted only in millimeters in SI units, and you will use the corresponding formulas. If your D value is between these values, then Kb is equal to this value. Between these values, it is this value. Okay. In most design situations, you are going to see that the diameter of the shaft or some other specimen is not known initially. You are supposed to calculate or design for the diameter of the shaft. So since you do not know what is the diameter or which one to use, so usually what we do is initially we assume Kb equal to 1, do the calculations, and then we get the diameter value. Then we again go in and modify the endurance limit with the small Kb value, Merin factor being modified, and then we do the calculations for diameter again. So this is how we do the design. Okay, so let's See, for a rectangular cross section, I do not know what is the diameter for a rectangular cross section. What do? We have to find an equivalent diameter for a rectangular cross section, and that is based upon some assumptions. So what is the assumptions? So first, for parts that are not round or rotating, an equivalent round rotating diameter is obtained. So usually we do not solve always for shaft problems. You may have a beam which is subjected to fatigue, and if you have a beam with a square cross section or a rectangular cross section, then you will be dealing with this kind of issues. So what do we do then? Here, equate the volume of the material stressed at and above 95% of the maximum stress to the same volume in the rotating beam specimen. So what do we do? Again, read, equate the volume of the material stressed at and above 95% of the maximum stress. So for example, if you take a beam and you find the maximum stress as sigma max, you find the areas of the cross section of the beam which has the stress value greater than or equal to 0.95 times sigma max values, and only those cross section value you convert it and into an equivalent amount of rotating beam specimen. And how do we do that? So they are doing some derivation here. Forget about the derivations. We need the final equation, and this is the equation we are interested in. So if you have the dimensions of your beam cross section as width b, height h, use these values in this equation and you will find what is the equivalent diameter. Use the equivalent diameter in the kb value over here and calculate what is the Merrin factor kb. Okay, so again all these are straightforward. You are also given what are the equivalent areas and how to calculate DE values. The formulas are directly given here. So based on these formulas, you can again evaluate them. I'm going to skip this. Again, direct application of the formula. The data for which SE prime value is published in your book is usually for bending moment load. Okay, but experiments could be done even with axial and compressive loads, and SE prime value could be published for it. But in our case, it is only for bending moment load, SE prime value, and because of that, Kc is equal to 1 if only a bending moment load is applied on your component. However, if you apply only axial and compressive loads, then the Kc value to be taken is 0.85. If you apply only torsional load, then you will apply Kc value equal to 0.59. Okay, again I stress, if you apply only axial load, then 0.85. If you apply on the component only torsional load, then you apply Kc equal to 0.59. What if I have a combination of values, axial and torsional, maybe axial and bending? What is the Kc value I should apply? In those cases, you will always take Kc equal to 1. If you have combined load, Kc equal to 1 should be taken, and there is a way to deal with the stresses. So for the combined load, we usually find the von Mises stress, right? Von Mises stress. This is the stress we will find, and there is an equation for finding von Mises stress which includes all these factors. We are going to see that equation later. Okay, so therefore in combined loading cases usually we take Kc equal to 1. Is this clear? Only in the combined loading case Kc equal to 1. But if you have purely axial load, Kc equal to 0.85, purely torsional load 0.59, purely bending load, then it is 1. Okay. Kd is the temperature factor. For any temperature which is above the room temperature is taken to be 20 degrees centigrade according to this table. We will take the value 1. Okay, what is the value? Kd equal to 1. So this term is nothing but Kd. If it is 50 degrees centigrade, this is the value of Kd, etc. So these are the different values which are provided. We can also calculate Kd by a different formula. The formula given here is this guy, Kd equal to, given in terms of temperature here. What is the temperature? Temperature is given in Fahrenheit scale, not in any other scale. In this formula, you will substitute only in Fahrenheit scale. So how do I convert other scales to Fahrenheit scale? I will give you a simple method to figure out the relationship between any temperature scale. For example, degree Celsius or Fahrenheit or Kelvin scale. So what is the formula we will use is the whatever the temperature we have, okay, whatever may be the scale. So we can say temperature minus the let's say the temperature of the melting, not a melting point, yes, melting point of water, melting point of water divided by the boiling point of water. It could be whatever scale. It could all these temperatures could be in whatever scale we want. Could be in Kelvin, could be in Fahrenheit, could be in Celsius. But consistently, if you choose Celsius, all the temperatures must be in Celsius. If you choose Kelvin, all the temperatures in Kelvin. And if you choose Fahrenheit, all the temperatures in Fahrenheit. Melting point of water. This ratio is always constant in all these scales of temperature. So if I write F in Fahrenheit scale, temperature in Fahrenheit, F minus in Fahrenheit scale, melting point of water is 32, boiling point is 212. This should be equal to in degrees Celsius. So if it is in Celsius C, temperature must be, unknown temperature must be in C, minus melting point of water is 0. We know it is in degrees Celsius, it is 0. And the boiling point of water in degrees Celsius is 100. 100 minus 0. So we get directly C over 100. In Kelvin, we can write the same kind of formula. Temperature in Kelvin minus the melting point of water, 273.15. Okay, 15, that's the value. The boiling point is 373.15 minus 273.15. So this is the formula. So you can, using this formula, this ratio, you can convert from one scale to another scale. Okay. So you can convert it into Fahrenheit scale. If you are given in Kelvin, convert to Fahrenheit. If you are given in Celsius, convert it into Fahrenheit, and then you can use this formula to evaluate what is the Kd value. So if I give you this formula in the formula sheet, you will have to convert it into Fahrenheit based upon these equations. So again, I'm not going to solve it. You can solve it by yourself. Very simple case. Ke is usually obtained from some graphs, and we obtain it through the table given here. So you are given 50% reliability, 90, 95, 99, etc. These are the standard reliabilities which will be given in most problems, and then you can evaluate, you can find out what is the Ke value from these tables. If you are given 98% reliability, use interpolation, linear interpolation between the values to figure out what is the KE value. KF is due to other factors, miscellaneous factors. The miscellaneous factors could depend upon your manufacturing processes. Manufacturing processes could create residual stresses and change the SE value. Then KF will be modified. Directional characteristics. If you have an isotropic material, results for isotropic material in the case of SE prime values, but during manufacturing process you turn it into a anisotropic material, then again your SE prime values are going to change largely, and it depends upon the KF value. If you do case hardening, this is another manufacturing process. For most fatigue applications we will do this. What is case hardening? You are making the external surface of the material very hard. If you make it very hard, then it will be scratch proof, and actually it will improve the fatigue properties of the material. Okay, so this again increases the SE value, and KF value most probably will have a value greater than 1 in the case of case hardening. Corrosion will degrade the material, so because of the degradation of the material, again SE value will go down, KF value again has to modify that. So again different conditions are given here. So we do not have much data regarding this. In big industries they might do experiments and then they may figure out what is the KF value, appropriate KF value to be used in different applications. So we are done with the Merin factors. Now we go to the next topic, which is the stress concentration factor. In the case of static loads, if you recall, we used KT value and the KTS value, and these were extracted from your Peterson's graphs. Now in the case of fatigue, we cannot use the KT and KTS value directly. Rather, we have to use what is called as the fatigue stress concentration factor, KF and KFS values in the case of shear loads, or shear stresses rather, to be more accurate. Okay, so how do I find KF and KFS values? The KF and KFS values usually depend upon KT and KTS values. So first step is to figure out KT and KTS values from your Peterson's graph. After you figure out what is KT and KTS values, then you will use a formula to evaluate what is KF and KFS. To evaluate KF, we use the formula given here. KF is equal to 1 plus Q times KT minus 1. What is the Q? Q is called as the notch sensitivity factor or notch sensitivity. Okay, so this notch sensitivity is usually takes a value from 0 to 1, and it is determined from the graph. So the graph here tells you what is the notch sensitivity. So this is similar to your KT and KTS values, but the values have to be obtained from different graphs, and these graphs will again be provided. Q and QS values, Q shear values will be provided for you. Depends upon the notch radius given in millimeters or in inches. You can see millimeters here, and the same values are given in inches, and the Q value on the y-axis. You have to extract it from here. What is the notch radius? For example, mostly in the shafts you have a shoulder, and on the shoulder you will have a curved edge, and instead of having sharp corners here, you will have a radius here, and this radius is the notch radius. So if you are given what is the notch radius, mostly in millimeters, then you can extract it from here. If it is 2 millimeters, and let us say our SUT value for the steel specimen. So for steel specimen, we are given these 4 curves with various SUT values. SUT values are again given here in English units, in SI units. So in SI units is 400 megapascal or 0.4 gigapascal, etc. So based upon these values, you can extract. If you have a value, let us say 620 megapascals, that means it is between 0.4 and 0.7, the value. And let's say the notch radius is 2 millimeters, then you will have to approximately get the value of Q from this graph, so some value in between, okay, maybe 0.75. So your Q value will take 0.75 value, you will extract it approximately, and then calculate what is the fatigue stress concentration factor. Your fatigue stress concentration factor is modified by the value Q. So usually your Kf value is always in between the values given here, between 1 and less than or equal to Kt value. Okay, your Kf value reaches a maximum value of Kt, and the minimum value is 1. So if you substitute Q is equal to 0, you get Kf is equal to 1. If you substitute Q is equal to exactly 1, then you can clearly see from the equation Kf equal to Kt. Okay, in the same way, for shear stresses, you will use KFS. We will exactly see how we use these terms in the later slide, but KFS can be figured out from this equation here again, with Q shear value extracted from this graph. In both these graphs, you can see curves for steel, and there is a curve for aluminum alloy. Okay, the dotted line is for aluminum alloy. Q for steel can be also only for steel. These equations are only for steel. In the case of steel, we can extract it from these equations here. You can use any of these equations also to obtain what is the Kf value. Again, the formula for Q is given here, square root of A over R. How do I find square root of A? Square root of A can be found from these formulas. If you have a bending load or axial load, then use this formula. If it is a torsional load, then use the formula given here for shear. Okay, so this is, if you substitute for torsion, you will get Q shear value. If you substitute for bending or axial load, then you will get the Q value as usual. Okay. Let's see for cast irons. Cast irons are usually brittle materials and usually subjected to compressive loads. Okay, and they are full of discontinuities because it is a brittle material. They will have a lot of discontinuities or micro cracks within them, and additional notches or change in geometrical features do not add too much harm to the component. So usually recommended value for Q value is 0.2, standard value for cast irons. Okay, so what do we have here? How to estimate Kf and the KFS values? You can use the formula or the graph. Again, I'm not going to solve this problem. Direct application of the formulas or extracting the values of Q from the graph. You can do that by yourself. Okay. Now let's see how to use the Kf and KFS values. Now my recommendation is use Kf always as the multiplier to your stress. Just like in the static case, for brittle materials, we always use stress in terms of Kt times whatever formula you have for stress, sigma nominal, or for shear stress, Kts times tau nominal, whatever formula you had for calculating the shear stresses, you will use that. We always use Kt and Kts as a multiplier to stress. In the same way, we are going to use Kf as the multiplier for your nominal stress. Now, in the case of fatigue applications, we calculate sigma A, sigma mean stress values, or tau A and tau mean. If it is a combined load, then we will calculate sigma prime A, which is the von Mises amplitude, and the von Mises mean stress. In all these cases, just use Kf as the multiplier to it in the formula, just like this. Okay. Now, in all situations, I recommend using Kf or Kfs values as a multiplier. But in certain situations, especially if we are much below the yield stress value, especially if we are within the much below the yield stress limit, then Kf can be also used in a slightly different way, just like a Marin factor for reducing SE values. So what do I mean? Here we have seen the formula for calculating the actual SE value. Marin factor is Ka, Kb, etc. up till Kf times SE prime. With this, we can also divide it by capital Kf value, especially if we have only a single load. Okay, if we have a combined load, never use this as a reducer for SE values. That's what being stated here. Okay, don't divide by Kf. If you have a combined load, never do this by this method. If you have only a one-dimensional load, or only bending moment load, or only axial load, then we can use this method. Otherwise, no. For infinite life, either method is equivalent, since so for very low stress values, we can divide by Kf here for your SE, or we can use Kf as a multiplier for a sigma. So either method is same, especially if we are much less than the yield point. My recommendation, never go with this method anywhere. Always use Kf as a multiplier. Okay, so that way we did not worry much about the problems. Okay, so let's see this example problem here. For a step shaft shown in the previous example 6.6, it is determined the fully corrected endurance limit is already given. SE is equal to 80 megapascal. Consider the shaft undergoes a fully reversed nominal stress in the fillet of the nominal stress. So you are directly given this. Estimate the number of cycles to failure. So this is a problem given here. We are given a example 6.6. There is a stepped shaft. Okay, so let's see here. The Kf value is estimated here. A steel shaft is in bending moment load, has an ultimate strength 690 megapascal, shoulder fillet of 3 mm radius, connecting a 32 mm diameter to 38 mm diameter. So what is the shaft? So try to solve this simple problem and then we can leave for the class. So we have a shaft with a larger diameter, 38 mm diameter, and let's see, stop slipping. So let's use home reduction, maybe radius. So I'm exaggerating the reduction. So here this is the 38 millimeter, and we have 32 millimeter here. So 32 millimeter radius. We have a radius, fillet radius R here is equal to 3 mm. Okay, so the diagram is not to scale, just to show there is a change in diameter. Okay, so first we need to estimate KF and KFS values for this problem. Since this is a bending moment load, only KF load. Let's see the case here. Okay, so it's the same problem with the bending moment load. So how do I determine what is KF? I have to use this formula. KF is equal to 1 plus Q times KT minus 1. Why do I need KF? Because I need the fatigue stress concentration factor to find the maximum stresses. Okay, KT minus 1. Now if I go to the Peterson's graph, I can extract KT. Okay, so go to A15.9 and you will be able to extract KT based upon what values, the D over D ratio, etc. I'm not going to go through that again, so I'm going to assume we already extracted this value KT. Okay, now we need to, based upon the fillet radius R, we need to get the value of Q. There are two ways. One, we can extract from the graph, or we can use the formula. Let's extract from the graph. That's easier. So the fillet radius is 3 millimeters, and this is where we are. And the SUT value, we need the SUT value for the problem, 690 megapascal, so nearly 700 megapascals. So we have the 700 megapascal curve here with 3 mm. We can approximately say it is 0.85. Okay, so Q is equal to 0.85. That's the value we are going to use. I think even in the example they have taken 0.84, so let's assume it is 84 in that case. Okay, so substitute in the formula, figure out KF 1 plus 0.84 times 1.65 minus 1, and if you calculate that you get 1.55. Okay, so having obtained the KF value, we can calculate the other quantities. This is the completely reversible load applied on the specimen, 260 megapascal. So sigma A is equal to 260 megapascals, and this is also equal to sigma max for completely reversed load. Okay, what else we need? We are given SE value. Now this is not SE prime value, rather SE value, which includes Ka, Kb up till Kf multiplied with SE prime value. This value is already given to you, 280 megapascal. Okay. Now, what you are asked in the question, estimate the number of cycles to failure. Okay. Before we go there, we have to use the Kf value to find the SF value. Okay. Again, if you recall, previously we solved the problem here using the equation SF is equal to A times n raised to the power b. That is the formula we have. This is the example problem we have solved. This is the formula to be used. That means I have to figure out what is the fatigue fraction, etc. Just like before. Again, I'm not going to solve it. I'm not going to solve the entire problem. I'm just going to show you from where we find the SF value. SF value is going to be based upon the fatigue stress concentration factor. We use it as the multiplier to the sigma A value above. So 1.55 times sigma A is 260. So that gives you a value of 403 megapascal. Okay. So now using the SF value, you need to determine What is the number of cycles to failure? What is the formula to be used? SF is equal to A times N raised to the power B. A and B you will have to find out. This should be equal to 403. Use the same formula as before. Find fatigue fraction F and then A and B values and then figure out what is the number of cycles to failure. So here it is already done. Fatigue fraction is found. A and B values are figured out. And then we find the number of cycles to failure and we get 32,300 cycles to failure. Okay. And clearly this is between 10 power 3 to 1 million cycles. Again, different kind of problem. We have 1015 hot rolled steel bar, which is machined to 1 inch. It is to be placed in a reversal axial loading for 70,000 cycles to failure in an operating environment of 550 degrees centigrade. Using ASTM minimum properties and reliability of 99%, estimate the endurance limit, the fatigue strength, and the fatigue strength at 70,000 cycles to failure. So this problem, we will solve it completely next class. Any doubt up till this point? Do you guys have any doubt up till this point? If you don't have any doubt, I'm going to stop here and we will meet again next class. Okay? Are you there?
Yes, clear, Doctor.
Okay. So next class we will do a revision for your exams, and then if time permits we will continue with this particular chapter. Okay, see you guys and I will meet you on Thursday.